Hi everyone, welcome to AI Crack channel. This is Akash Kangwar and today we'll be studying matrices and determinants lecture 2. So again, this is a theoretical lecture, so we'll keep it short and from next lecture onwards we'll start doing problems. So let us first talk about multiplication of matrices and we do it by row by column. Okay. So what do we mean by that? And first of all, let's try to understand when can we say that AB exists. So it's not like we can multiply any two matrices. There has to be certain conditions met after which we can say that AB exists. Okay. So basically, if the order of A equals to M cross N and order of B is N cross P, then only we can say that the AB is existing. So basically, number of columns in matrix A equals to number of rows in matrix B. If they are both same, in that case only we can say that AB is existing. Otherwise, AB won't exist. We cannot multiply them. Okay. Now let's see how can we multiply two matrices. Let's say I have this A matrix as A, B, C, D and I have this B matrix as E, F, G, and H. So what basically we do, we multiply row by column. Okay. So this is our row and I'll multiply with this column term by term. So what do we mean by term by term? So I'll explain that in this matrix format. So what I'll do, I'll write AB over here, comma B, and I'll write C, comma D over here. I'll write EG over here, but like a row, and FH over here like a row. Okay. Now what we'll do, I'll multiply A and E plus B and this is G, B and G. Okay. Now again, I'll multiply A and F and add B and H, C and E plus D into G, and C and F plus D into H. I tend to remember it with this method or a different method. You can also use your own methods to find out the final multiplication matrix, but this is this is what we mean by row by column. Okay. Now let us talk about properties of matrix multiplication. The first property says that matrix multiplication is not commutative. So that is AB is not equal to BA in general, right? They might be equal in few cases, but they are in general not equal. And they might not even exist together. So if AB is existing, it might be possible that BA is not existing. So forget about them being equal after multiplication. They might not even exist together. Okay. Now, if AB equals to O, this is a null matrix. This is not zero. This is null matrix, and that doesn't mean A equals to O or B equals to O. So in our regular algebra, what we used to do is if the product of two variables equals to zero, then we say that either A equals to zero or B equals to zero. That regular algebra is not applicable over here. Why? I'll tell you why. Now, if AB equals to O, then it might be possible that we have certain rows and columns in A and certain rows and columns in B, which after multiplication and doing this row by column, that become a null matrix, right? So we cannot say for sure that A should be zero or B should be zero. It might be possible that just the product is zero and both of them individually are not zero, not null matrix, not exactly zero, not a null matrix. Okay. But the reverse is true. If A equals to O, B equals to O, then AB equals to O. So if one of the matrices is O, then definitely if I'm doing this kind of multiplication, if all these terms are zero, then definitely the remaining terms would be zero as well after multiplication. Okay. Now third property is if AB equals to AC, that again does not necessarily mean that B equals to C. Let's see why. If AB equals to AC, so I can take AC over here and this becomes null matrix, right? And with the help of distributive property, I can write this as A times B minus C equals to a null matrix. Now we saw that if product of two matrices is O, that is a null matrix. We cannot say for sure that this is zero or this is zero. So B minus C is some, let's say D matrix. So A dot D equals to a null matrix. So D cannot be, might be zero, might not be zero. So we cannot say for sure that D is zero. What is D? B, that is B minus C. So if B minus C cannot be zero or null matrix, so basically B might not be or might be equals to C. So we cannot say for sure that B equals to C. So you have to be very careful while doing such questions. But again, if B equals to C, then definitely if I multiply anything, pre-multiply or post-multiply, basically, if I multiply any matrix to both B and C, then definitely the product would be equal. But in case of pre-multiplication together and post-multiplication together, it's not like I'm writing AB equals to CA. That might not be true. But definitely AB equals to AC. if A, B, C are, if A matrix, B matrix, and C matrix are comfortable or conducive product A, B, and B, C, then uh, these are valid. A dot B dot C equals to A dot B dot C with the help of brackets. Basically, these are associative, and similarly, these are also distributive. So that's kind of obvious. You can just take three matrices and try to prove it. You'll be able to get the same answer. Now again over here, these two properties are quite obvious. A square A equals to A dot A equals to A dot A dot A equals to A cube. That is again very obvious. You can just take one matrix and try to prove it. That would give you the answer. And similarly for this one, again, algebraic rules work over here in this particular property. A raised power M dot A raised power N equals to A raised power M plus N. And A raised power M times N. A raised power M raised power N equals to A raised power Mn, right? So these three properties are actually just like algebraic properties. Until now, what we have studied these three unique properties where normal algebra might not work. But the remaining properties which we have studied, algebra might work very well. Okay. Now this is again a similar kind of property. A raised power 0 equals to In. In is nothing but identity matrix. So let's say A is a square matrix of order, let's say 3. If I raise power it to 0, then I'll be getting 1 0 0 0 1 0 0 0 1. This is the I3. Okay. Now the interesting part over here is A raised power 0 is not defined if A is a null matrix. So basically, if A is a null matrix, then we cannot define A raised power 0. But over here, A should not be a null matrix, and that raised power 0, that would become an identity matrix. Okay. Now, since we have understood basic properties of matrices in case of both multiplication and addition, now let's try to look at some different kinds of matrices. So the first one is periodic matrix. So this is how a periodic matrix is being defined. A raised power k plus 1 equals to A. Now you must be wondering why not A raised power k equals to A, and then we can say this is a periodic matrix. So take this case. If I put k equals to 1 over here, then I'll be getting A equals to A. So this is as good as saying x equals to x, and now this function is periodic. That's not true, right? That doesn't make any sense. So this is as good as saying that. So that is why we keep A raised power k plus 1 equals to A, and if k equals to 1, then we have A square equals to A. If k equals to 2, then we have A cube equals to A, right? So this is how a periodic matrix is being defined. So k is called a period of matrix A, right? Now let us talk about a special case of periodic matrix, that is idempotent matrix. In this case, k equals to 1. Now why this is special? Because if I write A square equals to A, now if I try to write A cube, then that is nothing but A square dot A, and A square equals to A only. That would become A dot A. That would again give me A square. Now A square is again A. So if A square equals to A, then A cube, A raised power 4 equals to A raised power 5 equals to A. You can prove that. You can prove that if A square equals to A, then A cube equals to A4, A raised power 4 equals to A raised power 5 equals to all of them are A basically. But that is not true for k equals to 2 or k equals to 3. So let's say we have A raised power 3 equals to A cube equals to A. Now, if I try to find out A raised power 4, that would give me A raised power 3 dot A equals to, and that would A cube would become A dot A, and this would become A square. So A raised power 4 is become A square. But in the idempotent case, in this case where k equals to 1, in this case the every subsequent power is becoming A only. So if A square equals to A, that is why A cube equals to A4 is equals to A raised power 5 equals to A. Every power of A would become A only, and that is why this has been named different, and that is why this is special. Okay, that is not true for any other k value. Now let us talk about nilpotent matrix. So the condition is A raised power n equals to O, and A raised power n minus 1 is not equals to O. So what does that mean? Why this condition is very special? So let's say we have A cube equals to O. Then if I multiply A both sides, A dot O, that would become O only, because any product, anything multiplied with O is O only. And this becomes A raised power 4 equals to O. Similarly, we'll be getting A raised power 5 equals to O, A raised power 6 equals to O. Now this condition comes into picture. Let's say if I take n value, I just look at A raised power 6 equals to 0 and say that, okay, this is nilpotent matrix. Then I write n equals to 6. Then I try to find out A raised power 5, and then I also get 0, or not 0, O, a null matrix. So according to this, I'll get n equals to 5. So I'm getting two values of n. So that is why this condition is very important. So over here, a cube equals to O, and we cannot say that a square equals to O. So a square equals to some, let's say, B matrix, and that is not a matrix. If this is the case and this is the case, then n equals to 3, and that is the correct answer for nilpotent matrix, right? Then only we can see that this a raised power n is n equals to 3 over here. Okay. Now let us talk about involuntary matrix, and the condition is a square equals to in, where n is the order of square matrix of A, right? So if I multiply A dot A, and if I'm getting n is the order of square matrix of this only. So if we are getting this, then basically that is called as involuntary matrix. Okay. Now the last one is orthogonal matrix. A square matrix is said to be orthogonal matrix if A dot A transpose equals to I equals to A transpose dot A. Again, this is valid for square matrix. Now first, let's see how to find out the transpose matrix. Okay, so let's say we have this A matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have to find out the A transpose. Now what I'll do, I'll place a hinge over here. I'll look at the diagonal elements only. I'll place a hinge over here. I'll place a hinge over here. I'll place a hinge over here. Okay. And I'll take this entire row. I'll take this entire row and I'll take this entire row. What I'll do when I'm placing the hinge over here, I move this in the clockwise direction. I move this entire row in the clockwise direction. So that becomes 1, 2, 3. So this was horizontal and I moved it in the clockwise direction by placing hinge on the first diagonal element. I got the first column of A transpose. Similarly, now for the second row, I'll place the hinge on the diagonal element and again I'll move it in the clockwise direction. This one goes here, this one goes here. That becomes 4, 5, and 6. And similarly for this one, I'm placing hinge over here and this will move in the clockwise direction. That becomes 7, 8, and 9. So this is how you have to write the A transpose matrix. You can remember in your particular peculiar method. I can remember in this particular method if I forget it by any chance. Right. So if A dot A transpose equals to in equals to A transpose dot A for any square matrix, n is the order of the square matrix of A, right? So if this particular condition is being satisfied, then we can say that A square matrix is the orthogonal matrix. Now let us talk about the transpose and its properties. So the first four properties are very obvious and basic. So you can derive it by yourself. I'll take one example. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our A. Now let's try to find out A transpose. I'll be getting 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now if I find out A transpose basically, I'll be getting 1, 4, 7, 2, 5, 2, 5, 8, and 3, 6, 3, 8, 9, 3, 8, 9. Sorry, this is 3, 6, 9. Okay. Now you can clearly see that this matrix is same as this matrix. Okay. So you can similarly prove all the other properties. The only important property for transpose is this one. AB transpose equals to B transpose A transpose. You know that in product the order matters. So we won't be writing as A transpose B transpose. This is not correct. We have to write AB whole transpose equals to B transpose A transpose whenever we have to expand it. Okay. So this is the most important property of transpose. So today's lecture was till here only, and in the next lecture we'll be talking about certain examples, and also we'll start the properties of determinants, and after that we'll study the system of equations. So let's meet tomorrow. Thanks for watching.